Today, we are going to focus on noise sources, isolation and control. Now, we are thinking about industries where manufacturing plants, construction sites, or even power generation facilities, many of them often come to our mind beside impressive machineries and bustling activities. That is, the noise. It is just a general hum. Industrial environments are often characterized by a wide array of specific and often intense sound sources. In this video lecture, I am taking you a closer look at what these sources are. We will explore different type of equipment, processes, activities that contribute to the overall noise level within and around industrial facilities. Understanding these sources is the first crucial step in effectively managing and mitigating industrial noise pollution. As of we know, we can give significant impact on both the workforce and surrounding communities. So let's get started and unravel the various contributors to the soundscape of the industry. Let's delve deeper into nature of industrial noise. Understanding fundamental characteristics of this noise is key to address its effects. First, we have noise generation. Industrial noise isn't just one homogeneous sound. It arises from various mechanisms. We often encounter mechanical noise, which stem from the movement and interaction of machinery parts. Thinking of the clanging of gears, the vibration of motors, or the impact of hammers. Then there is fluid noise, generated by the fluid of liquid or gas under pressure, like the hiss of compressed air or rush of fluids in pipes. Lastly, we have electromagnetic noise, which can sometimes be emitted by electrical equipment, although this is often less dominant in the overall industrial soundscape compared to mechanical and fluid noise. Moving on to the factors. Intensity and our perception of industrial noise are influenced by several elements. The type of source itself plays a crucial role. A jackhammer will inherently produce more intense noise than a conveyor belt. Our distance from the source is also a significant factor. As we move further away, the sound intensity generally decreases. Finally, the working equipment itself, including the presence of wall, ceilings, and other structures, can affect how sound propagates and it is perceived. Let's consider sound fields. Industrial noise can travel to our ears in different ways. Airborne noise is what we typically think of sound wave traveling directly through the air from the source to the receiver. However, we also have structure-borne noise, where vibrations are transmitted through solid materials like floors, walls, and machinery frames, and these vibrations can then radiate sound into the air. Further, the way sound behaves in an environment is influenced by diffraction, that is, bending around obstacles, reflection, bouncing off surfaces, and absorption, being soaked up by materials. This phenomena significantly impact the sound levels we experience in different locations within and around industrial site. Finally, the control needs. Given the complexity of industrial noise generation, propagation, and impact, systematic approach to control is essential. A source ranking study is often a vital first step. This involves identifying and prioritizing most significant noise sources to focus mitigation efforts where they will be most effective. Let's now consider the driving forces and noise implications. It is important to recognize that the generation and management of industrial noise aren't isolated issues. They are intertwined with broader economic, environmental, and operational factors. First, economic development is a significant driving force. push for cost-effective production often leads to adoption of high-speed machinery and processes, which unfortunately can be major contributor to noise generation. The need to maximize output while minimizing cost can sometimes inadvertently exacerbate noise problems. Secondly, there is growing environmental focus. Reduce the noise around environmental, that is, the resources conservation and minimizing environmental impact are increasingly important consideration for industries. While this often leads to positive changes, it can sometimes have indirect noise implications. For instance, the adoption of certain energy efficient technologies might introduce new or different noise characteristics. Next, personal exposure. It is a critical concern. Regulation and ethical considerations necessitate limiting the amount of noise workers are exposed to. When noise levels exceed design limits, it poses risk to hearing health and can impact productivity, well-being, making noise control a vital aspect of occupational safety. On the other side, we have manufacturers' goals. Industries are constantly striving for lower space, material and energy use, as well as increased productivity. These goals can sometimes lead to design and operation of more compact and powerful machinery, which can inherently generate higher levels of noise. This brings us to the noise challenge. A common reality in industrial setting is that higher output often means more noise. As production rate increases, machinery generates more frequently at higher speeds, leads to elevated sound levels. This creates a direct conflict between production efficiency and noise control. Finally, there is noise rise. The relationship between operational speed and noise isn't always linear. Often, noise levels increase non-linearly with speed increases. This means that even a small increase in the operating speed of machinery can result in a disproportionately larger increase in the noise produced, making it crucial to carefully manage operational parameters from a noise perspective. Building upon our previous slide discussions about the non-linear relationship between speed and noise, in this slide I am going to discuss you about speed increase and noise emissions. Let's take a look at some of the examples. For rotating print machines, a speed increase can lead to a substantial rise of 7 decibel in the sound level. This might not seem like a huge number on its own, but remember that decibels are logarithmic scale, so even a 7 decibel increase represents a noticeable jump in perceived loudness. Next, moving on to warp knitting looms. The impact of increased speed is even pronounced, resulting in a significant noise increase of 12 decibel. This highlights how certain types of high-speed machinery can become considerably louder with even moderate increases in their operational tempo. Diesel engine shows a noise increase of 9 decibel with heightened speed, while petrol engine exhibits an even more dramatic surge of 15 decibel. These figures underscore noise challenges associated with increasing the power output and operational tempo of combustion engines commonly found in industrial settings and equipment. Perhaps one of the most striking examples here is with fans, where a speed increase can lead to very substantial noise rise in the range of plus 18 to 24 decibel. This broad range indicates that the sensitivity of fan noise to speed variation can be quite high, depending on the specific design and operating conditions. Finally, the slide reminds us that is fundamental principle in acoustic sound power doubling corresponds to a rise in 3 decibel. This benchmark helps us contextualize the larger decibel increases we see in the specific environment examples. For example, 6 decibel increase would represent quadrupling of sound power. What these figures clearly illustrate is that even seemingly small increases in the operating speeds of industrial machinery can lead to significant escalations in noise emission. This reinforces the importance of carefully considering the noise implication when designing processes, selecting equipment, and managing operational parameters in industrial environments. It also underscores the need for more effective noise control measures. Let's talk about cost-driven shift and new technologies, how they impact industrial noise, keeping it straightforward. First, cost effects. Sometimes to save money, industries might switch to production methods that are actually louder than what they used before. Cheaper doesn't always mean quieter. Next, new tech noise. Newer technologies like those using phase sequence drivers can sometimes make noise levels even higher than older systems. Progress doesn't automatically mean less noise. Then we have sound radiation. Simply put, bigger machines often have larger surfaces that vibrate and create more sound. Size can contribute to the noise problem. Finally, emerging challenges. Modern technology, while bringing many benefits, can also introduce entirely new types of noise issues that we need to understand and address. New technology, new sound, new problems are to solve. So, in short, the drive for lower cost and the adaptation of newer technology can sometimes unintentionally lead to increased or different types of noise. We need to aware of these potential downsides as we move forward. Let focus on specific type of industrial noise, that is mechanical noise from vibrating sources or surfaces. A significant portion of noise we encounter in industrial setting originate from the vibration of machine component and structures. To understand this better, let's look at the sound power formula. It is given here. This equation tells us the sound power radiated by a vibrating surface. Let's break down the parameters. Here it is rho density, air density, which influences how easily sound wave propagate. C is the speed of sound in the air. S denotes vibrating area of the surface. As we touched upon earlier, larger vibrating area generally needs to more sound radiation. Then V square is mean square velocity of vibrating surface, essentially a measure of how intensity the surface is vibrating. Higher vibration velocities result in more sound. Then sigma suffix radians, it is radiation efficiency, which describes how effectively vibrating surface converts its mechanical energy into sound wave. This depends on the frequency of vibration and the shape and size of the vibrating object relative to the wavelength of the sound produced. Understanding these parameters give us clues about reduction strategies. To minimize noise from vibrating surfaces, we can aim to reduce the vibrating area. Designing smaller or more compact machinery can help. Using the damping materials, applying materials that absorb vibration energy can significantly reduce the mean square velocity and thus radiated sound. Block the forced vibration. Isolating machinery from its surroundings or modification, the excitation forces that cause vibration can prevent or minimize the transmission of vibrations to larger radiating surfaces. Then at last, the examples of mechanical noise from different vibrating surfaces. They are eccentric rotating machines. Imbalances in rotating parts can cause significant vibration that radiate as noise. Panels acting as loudspeakers. Vibrations transmitted to large flat panels can cause them to act like loudspeaker diaphragms, effectively radiating sound. Impact induced vibration. Sudden impacts like hammering or collisions can set surfaces into vibrations, generating impulsive noise. In essence, this slide emphasizes the vibration of surfaces. It is a primary source of mechanical noise in industrial environment. Let we focus to another significant category of industrial noise, that is fluid noise, turbulence and flow. This type of noise arises from the movement of fluid, whether they are liquid or gas. Looking at turbulent sources, we can identify several common culprits in industrial settings. Moving, rotating solids interacting with fluids. Think about a fan blade cutting through air or an impeller churning a liquid. The movement of these solid objects create disturbances in the fluid, leading to turbulence and noise. High pressure discharge is another major source. When the fluids are forced through narrow openings or released at high pressure, resulting rapid expansion and turbulent flow generate significant noise. Examples include compressed air exhaust or steam winds. Finally, obstacles in flow can disrupt smooth fluid movement, creating eddies and turbulence. This can happen in pipes with sharp bend, valves or any obstructions that impede the regular flow of a liquid or gas. Next, we are seeing about sound power dependence. The relationship is often described by this formula, where W represents sound power generated and U is flow velocity. This sixth power of U is crucial because it highlights how incredibly sensitive fluid noise is to change in flow speed. Even modest increase in velocity can result in substantial increase in the noise produced. To put this into perspective, the doubling the velocity increases the noise by 18 to 24 decibels. This is a massive jump in sound level. Recall that a 10 decibel increase is generally perceived as a doubling of loudness. Therefore, doubling the flow velocity in a system can lead to perceived loudness increase of more than 4 times. Understanding this strong relationship between flow velocity and noise generation is vital for designing and operating industrial systems. By minimizing turbulence through smoother flow path, reducing high pressure discharges where possible, and carefully managing flow velocities, we can significantly mitigate fluid noise in industrial environments. Follow our discussion on the sources and dependence of fluid noise. Given the significant impact of flow velocity and turbulence on noise generation, the strategies here focus on managing these aspects. First and often, most effective strategy is to reduce flow velocity. As we just learned, sound power is highly dependent on velocity. By simply decreasing the speed at which fluids move through a system, we can achieve substantial reductions in the generated noise. This might involve using larger diameter pipes, reducing pump or fan speeds, or optimizing system design to minimize pressure drops. Next, use the diffusers to minimize turbulent force. Diffusers are designed to gradually expand the flow area, allowing the fluid to slow down more gently and reduce the formation of disruptive balance. This is commonly seen in exhaust systems or ventilation outlets where a controlled expansion of air or gas flow help to dissipate energy more smoothly and quietly. Another important approach is to streamline obstacles. Any sharp edges, abrupt changes in direction, or protrusions in a fluid flow path can create turbulence. By removing or smoothing these flow barriers, we can promote a more laminar, less turbulent flow, thereby reducing noise generation. This might involve rounding corners in duct, using more gradual bend in pipes, or redesigning internal components of valve and other flow control devices. Finally, the applications. Machinery noise reduction indicates that the principle of reducing flow velocity using diffusers and streamlining obstacles are practically applied in the design and modification of various industrial machinery to mitigate fluid related noises. Let's bring together some of the concepts we have discussed. Common industrial noise sources. This gives us a practical overview. Much of the noise in industrial environments actually originate. We can categorize these sources into a few key areas, that is mechanical parts, fluid and vibration, and other sources. Mechanical parts, these are the components of machinery that through their movement and interaction generate significant noise. Examples include rotors. The rotating parts in motor, turbine and pump can produce noise due to imbalances, friction and aerodynamic effects. Stators, stationary counterparts to rotors, can also contribute to noise through vibrations induced by the rotating parts or electromagnetic forces. Gears, meshing of gear teeth in transmissions and other mechanical systems is a common source of whirring, grinding and impacting noises. Next, we categorizing the fluid and vibration sources. First, fans. As we discussed, rotation of fan blade to move air or gases can generate substantial noise due to turbulence and movement of the blade themselves. Vibrating panels, large flat surfaces on machinery or structures can be set into vibration by internal forces or transmitted vibrations. Turbulent flow, chaotic movement of liquids or gas in pipes, ducts or around objects, as we explored earlier, is a significant source of broadband noise. Finally, we have other category of sources of noises in that impact process. Operations involving sudden collisions or impact such as hammering, forging or material handling generate impulsive and often high intensity noises. Electrical machines, while sometimes contributing to mechanical vibrations, electrical equipment like transformers and large motors can also produce humming or whining noises due to electromagnetic effects. IC engines, that is internal combustion engines, used in generators, compressors and various mobile equipment. These engines produce noise from combustion, exhaust and the movement of their internal parts. So this slide provides a good summary of the typical culprit behind industrial noises. By recognizing these common sources, we can better focus our efforts on understanding the specific noise generation mechanisms and developing targeted strategies for noise reduction. We came to our conclusion on this video lecture. These are some of the typical loud noises I just given you. They are crushing, riveting, blasting operations, definitely noisy stuff. Then you have got punching presses, drop forges, drilling, all that heavy work makes a racket, and things like pneumatic tools, plasma jets, sandblasting, lot of air and particles moving fast, so it is loud. Even regular machine tools, textile machines, filling machines can add up to a lot of noise. Now for the bigger picture, that is the conclusion. We have seen there are a lot of different things that can cause noise in industry. So it is really important to understand the basics of how sound works if we want to fix it. The key is to look at the source of the noise, how it travel, the path, who is hearing it, the receiver. If we can control the noise at any of these points, it will help. Really, it is about having a good plan to make our workspaces safer and quieter. That's pretty much lot of noise out there in industry, but we can understand where it is coming from. Thank you again for your engagement throughout this lecture. If you have any further questions or want to delve into specific aspect in more detail, don't hesitate to ask. We will see in the next video lecture.